Welcome back. When we left off last time, I asked you to answer these questions on your own. The first one, what is friction? Well, friction is a force that opposes motion between two surfaces that are touching. The three main types of friction that we talked about when it wasn't moving, when it was sliding, and when it was rolling. So static friction is between two surfaces that are not moving compared to each other. Sliding friction is between two surfaces that are sliding past each other. Fluid friction is when an object slides through a fluid, which is a liquid or a gas. So instead of two solids sliding past each other, it's just, you think it is just sliding through the air. The bow of the ship is sliding through the water, and actually the top of the ship is sliding through the air. Fluid friction is a type of sliding fluid, and in fluids, which remember are liquids or gases. The force that opposes the gravity is called air resistance and is a type of fluid friction. And we said it depended on three different things: the size of the object, okay, so the bigger it is, the more air resistance, okay, this is why you want a large parachute instead of a tiny parachute. The shape of the object, which is why parachutes spread out and they're not shaped like the end of a rocket or something, so you just like fell down. And then the speed of the fall, like when we watch the skydivers, the faster they fall, the more air resistance builds up underneath them, and eventually the air resistance equals the force of gravity, and they fall at a constant speed called terminal velocity. Newton's third law of motion. The first law, okay? Newton's first law of motion. And we already kind of looked at this when we looked at inertia, okay? And it says an object in motion, an object at rest, stay in rest unless acted upon by an unbalanced force, which is what inertia said. Inertia was the tendency of an object at rest to stay at rest, and the tendency of an object in motion to stay in motion unless acted upon by an unbalanced force. And remember, I said often the law of inertia is often, the first law of motion is often called the law of inertia. So it's often referred to as the law of inertia, okay, because they're saying the same thing. Okay? Inertia is just a measure of this tendency to stay at rest or to stay in motion. So what, breaking down Newton's first law, okay, the objects want to keep their motion, whether it is if they are moving, they want to keep moving. And if they're still, they want to stay still. And the only way to change this is to apply an unbalanced force. Okay? And inertia is the resistance of an object to any change in motion. So when we measure it, which we said inertia depends on mass, when we measure this tendency of doing this, it's inertia. Okay? And the only way to overcome that is to apply an unbalanced force. This, as we said, is called the law of inertia. Inertia is an object's resistance to changing its motion. Okay? And it depends on mass. So really, inertia just kind of measures the first law of motion. Car crashes are an example of Newton's first law in action, okay, and inertia. Okay, a passenger not wearing their seatbelt keeps moving forward at the original speed even if the car stops. So an object in motion wants to stay in motion. So if you're not attached to the car and the car suddenly stops, okay, if the car was going 70, you were going 70 in the car because you were moving relative to the car. So if it suddenly stops, you just keep going forward at 70 miles an hour. There was nothing to stop the person, no seatbelt, they're not attached to the car. So because they're two separate objects, the car's one object and you're another object. So if the car's motion changes, yours doesn't, and you just keep moving forward at the original speed. The person with a seatbelt slows is because they're attached to the car as the car slows down. So instead of being a separate object, okay, Now, by being attached to the car, you're part of that same object. So when it slows, you slow. The seatbelt provides a restraint. They're attached to the car on the person. This changes their motion to stop with the car. Okay, and as we said, this is an example of the law of inertia at work. Okay. In this little clip, we're going to take a look again at Newton's first law, which, remember, we said is often called the law of inertia.
Newton's first law has to do with objects at rest and objects in motion. He noticed that objects at rest stay that way until something comes along to move them.
So that cue ball is going to stay there at rest until something comes along, an unbalanced force, and makes it move.
He also noticed that objects that are moving continue to move in a straight path unless a force slows them down and stops them. Newton called this tendency of an object at rest to stay at rest, and the tendency of an object in motion to continue moving, inertia. You must overcome inertia in order to start an object moving. And you must overcome inertia in order to slow down and stop an object that is moving. So Newton's first law of motion states that if no unbalanced force acts on a moving object, the object will continue moving at the same speed and in the same direction. And if the object is not moving and at rest, it will remain at rest until an outside force acts on it. A spacecraft will continue moving through space at a constant speed and in a straight path without the need for engines. Because there is little matter in the vacuum or emptiness of space, there is nothing to slow the vehicle down. Once the craft is away from Earth's atmosphere and its gravitational pull, the engines can be turned off. It will continue at a constant speed and in a straight path. Only if the engine is fired again will the craft be able to change speed and direction.
So without friction in space, an object in motion stays in motion unless acted upon by an unbalanced force. This is how we've been able to send some of the explorers out to the edge of the solar system. The engines haven't been running for years and years. They just keep moving at a constant speed and in the same direction.
On Earth, objects are affected by outside forces that slow them down and eventually stop them. Even on very slippery surfaces such as ice, objects will eventually slow to a stop. Friction is the force that slows things down.
There's a second segment that I'd like you to take a look at, and they use some of the principles of inertia and an object in motion staying in motion in the movie that probably many of you have seen, Christmas Vacation. Quite often in movies, they'll apply the law of physics, but they'll exaggerate them. And in this scene from Christmas Vacation, the dad here is going to put this stuff on the bottom of his sled that makes it have no friction. And then Newton's law says an object in motion will stay in motion unless an unbalanced force acts upon it. So with no friction between the sled and the snow, then Newton's law says that he should continue in motion until an unbalanced force acts upon him.
This is a new non-caloric silicon-based kitchen lubricant my company's been working on. It creates a surface 500 times more slippery than any cooking oil. We're really gonna fly down the hill with this stuff.
Has anyone ever used it on a sled?
Not that I know of, Russ.
Well, don't go putting none of that stuff on my sled, Clark. You know that metal plate in my head?
How could I forget?
I had to have it replaced because every time Catherine revved up the microwave, I'd piss my pants and forget who I was for a half hour or so. So over at the VA, they had to replace it with a plastic one, and it ain't as strong, so... I don't know if I ought to go sailing down no hill with nothing between the ground and my brain but a piece of government plastic.
Do you really think it matters, Eddie?
Well, see, the plate runs right underneath my part here. And over here, it's, nothing. But here, if this gets dented, then my hair just ain't gonna look right.
I know the feeling. Well, I better try this first, see how it works.
Well, you be careful there, Clark. That's
Nothing to worry about, Eddie. Going for a new amateur recreational saucer sled land speed record, Clark W. Griswold Jr. Remember, don't try this at home, kids. I am a professional.
Later, dudes. Let her rip, ain't pen.
Object in motion stays in motion. So with no friction on the bottom of the sled, he just keeps going. A little bit of an unbalanced force. Here comes an unbalanced force.
bingo.
And then there's this last clip on train crashes. Trains have a huge mass, so they have a lot of inertia. They have a resistance to changing their motion. There's three little videos I wanted you to take a look at. And one of the things we said inertia depends on is the mass of the object. So in this first video, we see this school bus, and it has a lot of inertia. It has a resistance to changing its motion. Newton said an object at rest wants to stay in rest unless acted upon by an unbalanced force. But the train coming at it is an object in motion, and it wants to stay in motion and continue moving in a straight line unless acted upon by an unbalanced force. Now, one of the things we said inertia depended on was mass. Well, the mass of the train is much greater than the mass of the bus. So the mass of the train and its inertia is going to be able to overcome the bus's resistance to changing its motion. It just flipped it aside like it was a little toy. Now in this second example, it kind of shows the same thing. It also shows some law of conservation of momentum. It shows that the train is able to transfer its momentum or its inertia to the cars, and then each car is able to transfer its momentum and inertia to the next one.
At a railroad crossing in Chicago, the warning lights may be bright, but the driver of this truck certainly isn't. He thinks he can outrun a fast-moving freight train. Instead of stopping, he keeps on trucking.
Object in motion, like this train, wants to stay in motion. Okay, so it has inertia. It has momentum is the measure of inertia. So it's moving. Okay, now the truck is an object at rest, and it wants to stay at rest. It has an inertia to stay at rest. The inertia of the train is much greater.
But it's rush hour, and because of the line of cars ahead, he can't clear the tracks. And now this big rigger's in big trouble. The train smashes into the 18-wheeler, causing a domino effect.
Okay. Now, this domino effect is an example of the transfer of momentum. Okay, the momentum of the truck when it began to move went into the cars, and then from one car to the next car.
So exactly what happened here? The train expert describes the crack-up in technical terms.
It would look like a beer can getting hit by a gorilla. Just smashed it like it was nothing, like just effortless. It rocked the world for that moment.
Thankfully, no one was seriously hurt due to the trucker's stupid behavior. But at least he learned a valuable lesson. Only Superman is more powerful than a locomotive.
And this last one, train crashes are always kind of fun. Truck sitting here has inertia. It wants to stay at rest. It doesn't want to just begin moving on its own. A fast-moving train coming at it has inertia. An object in motion wants to stay in motion and wants to continue in a straight line in the same path. We're going to pick up here next time. I'd like you to answer these questions on your own.